thank you for everybody for attending during your summertime. So it's very exciting to see how many people are participating and interesting in the topic. So just before I start, I want to mention that, yes, it's a very, very interesting topic. And I was actually, about a year and a half ago, I didn't know much about causal inference myself. And the slides are actually a result of me learning the topic. And within my company, I created like a study group. I actually ran two of them. And this is kind of like my understanding of the topic. And I'm glad to pass this information over so that anybody's interested in learning and starting to add to ask their data why, that you'll know like how to start learning the topic. Just before I start, all the opinions expressed are my own and not of my employer. And if you want to follow along the slides, you can just, during this talk or after, these slides are always available, so feel free to access them over here. Oh, I shouldn't have pressed that. Let me just make sure I'm in presentation mode. Okay, should be fine. Okay, so just set up my screen 1 second. Yeah, so we put a lot of trust in data. For example, we use it in order to learn about medicines that we're willing to put in our bodies thanks to researchers examining, for example, proteins, or we feed data through machine algorithms for useful apps, like, for example, for navigation, or in order to infer like who gets recommended for a loan in a bank or not. And so data is king, data is key, data is quote unquote the new oil. But I feel that there's one overlooked question when it comes to how much trust we put in its data. And I really like the learnings from Judah Perl, who's considered the godfather of causality. He really like formalized the field of causality from a computer science perspective. And if there's one takeaway message I got from him, and that's the main takeaway message for today, is that the story behind the data is as important as the data itself. Data on itself is a first good step, but it's not useful until you truly understand how it has been collected. And so that is what I hope you take away today that you'll use within your analysis. And along with that, you'll have a few more messages. First of all, you'll be able to identify potential ways of misinterpreting the data. You might be doing that at the moment without realizing. So hopefully you'll be more educated about this by the end of the talk. And I'll introduce a very useful tool called graph models that helps visualize that story behind the data. And this is truly, and you'll get tools to start your first steps within the field of causal inference. The way I shape this talk is around anybody who makes data-driven decisions and are interested in going beyond the common correlations and associations to make better decisions using their data. Background in statistics is nice, but it's not essential because I'm very visual in how I portray the information. Thanks, Nicholas, for the background. So yeah, I came from and I was about 10 to 12 years in academia, and now I'm in the private sector. I've dealt with many types of data sets, from cosmology, biology, and now healthcare. So Judah Perl introduced what he called the causal ladder, and that's basically going from where most of us are right now, which is basically doing correlations. If it's basic statistics and machine learning, and what's called seeing, and as sentience, we learn from doing, and so the next stage is doing, and then really predicting the future. That's what's called imagining. And so what we'll do, we'll get back to this causal ladder at the end of the talk. That will be around over here. But so what I set up for today is we'll talk about why should we care about causality? Why should we go beyond correlations? Why isn't correlations just enough? And then we'll talk about Simpson's paradox, which is the classic case of misinterpreting of data. And then I'll introduce graph models and how we use it to visualize the story behind the data. And then we'll summarize, where I'll provide a whole lot of resources for those who really want to dig deeper. So we'll talk about the fact now that correlations, why they're limiting, and as a result, we'll either be inconclusive in our results, or even worse, we'll get misleading results. So I like this comic strip by XKCD, in which just reading it here, one person says, I used to think correlation implied causation, but then I took a statistics class, now I don't. So, so she says, sounds like the class helped. Well, maybe. And so to summarize this in 2 words is, was intervention of the class successful? And he is actually inconclusive. So, so that's anecdotal, but more seriously, let's look at actual data. So for example, here I'm showing like 2 data sets in which you can see that they're longitudinal, and you can see that they very well agree with the correlation that may be quantified as 95.2%. Okay, so does that mean that the 2 data sets are related? Well, that's not a fair question, because I didn't even tell you what the data sets were. So the data sets happen to be people who drowned after falling out of a fishing boat and marriage rate in Kentucky. And so it would really hard to believe that there's actually a causal link between them, and maybe there's something beyond. And so what we're looking at most likely is what's called a spurious correlation. So what does that mean more in detail? Well, we won't use that example. Here I'm going to use a different example, still within the theme of drowning. So let's say you work in a city council and they want to reduce their drowning rates at their beaches. And so they want to figure out, well, the intervention is going to be lifeguards. And the question is, well, when are we going to put the lifeguards? You kind of know the answer in advance, but let's pretend that we don't know. Let's pretend we're a computer. We don't know anything about anything. And so as a computer, we're fed a whole lot of data. And what we find is that there's a correlation between the drownings and ice cream sales. So we can, for example, visualize it in a plot like this, in which we can correlate drowning rates and ice cream sales. We see that there's this nice correlation. And the question that remains is, well, is this causation? So obviously we know it's not causation because we know the story behind the data. We're domain experts of drownings and ice cream sales. And we know that they have a common cause, or something that's called a confounding factor, which is the weather. And so if we color code these data points as weather, as if you analyze them on their own, you can see that there's no real correlation between them. Of course, this is a very simplistic picture. There might be more parameters. For example, the drownings is a function also of the intervention that we want, the lifeguards and people who are actually swimming in the beach. And ice cream sales depend on supply and demand. But the point is that there is this flow of information. There's this flow of information from ice cream sales to drownings that causes that spurious correlation. In order to resolve it, we need to control for a confounding factor, which is the weather. Let's look at another made up but plausible example. So let's say that you're an engineer and you want to improve the design of a fire alarm. Well, what sort of data do you want? Well, what you'd want is measurements from the fire. You'd want the temperature and the distance from the alarm. Is that it? Well, actually, it was a trick question, because you're not actually using, there's no such thing as a fire alarm. We only have smoke detectors, where the smoke is a proxy for the fire. You can imagine, for example, if you have a window open and you're blowing all the smoke through the window and nothing gets to the alarm, you're still going to have a fire in the building that's causing the smoke, but the sound alarm won't go off. And so in this sense, this is what's called a mediator variable that's between the fire and the sound. So that's something we have to account for as well. And now I'll give another useful example to have in mind. And it has to do with the link between smoking and lung cancer, where right now we know that one causes the other. That's why we have these warnings on cigarette packages, where in the past, a doctor was very clueless about this. Well, how did they go about understanding the causation between them? Well, let's start with the picture they had in mind at the beginning. They had some sort of correlation between smoking and lung cancer, but can they definitely like draw this arrow between them? Well, the tobacco industry said, well, there might be a confounding factor, right? We talked about confounding factors. So maybe one's DNA will cause them both to smoke more and have lung cancer, and then we'll have this flow of information like we had before between the ice cream sales and drownings. And even if this is true, the question is, if there's flow of information also directly from smoking to lung cancer, then there's a question, well, which arrow is stronger? Which has a stronger correlation? Is it this arrow or is it this arrow? And so we could potentially control for DNA. But remember, at the time, they didn't have access to DNA information. That was available only from year 2000. So still, how did they resolve this in the, I don't know if the 1960s or 1970s. So how did they resolve this? Well, what they found was they used a mediator variable, which is tar in the lung. So this is an observable, right? You can go to an X-ray and you can measure this. And so what you have is something called the front door path, which means that we don't have to collect information on the DNA. So this is very expensive even in today's term. And so we can just collect information on tar and smoking, and we can infer causality regarding effects on lung cancer. So here I showed the limitations of using only correlations and how we can use tools like confounding factors, like common causes and mediators in order to resolve for this. Now I'm going to go even further into something called Simpson's paradox, which shows how one can potentially misrepresent the results from the data. I do want to mention that all the data that I'm using is imaginary, but you can consider it plausible. You might have something similar in your analysis. And also for simplicity, assume everything to be statistically significant. So just, if you're not happy with the number, just multiply it times 1,000 or 1,000,000 or whatever. It doesn't matter. It doesn't change our results. I will also do something very questionable. I am going to confuse about 95% to 100% of the audience, but I promise you it is well worth the effort, because this is truly your first step into understanding causality. So do be prepared to have your mind blown. So the way we're going to learn this is through a made-up pharma study in which we have 2006 patients, which are equally distributed among control or treatment. So think of this as a randomized controlled trial in that sense. And the end result is that 58% of the treatment recovered and 72% of the control recovered. So how do we conclude from this? We do 58 minus 72, so that's minus 14. So that means less treatment recovered compared to the control. And so what you can conclude from this data is that the drug is deleterious and it should not go to market. So let's say we want to look a bit more deeper into the, and this is the way, just in a board meeting, you would present it to stakeholders. So let's dig a bit deeper into the data. And let's say we want to split it by gender. And so with the males, for example, we have 50 treatment recovered, 50%, and 40% of control recovered. So that's actually a beneficial measurement for the drug for males. And for the females, we happen to have the same 10%. And so what you have, interestingly, here is a contradiction in conclusions. And that contradiction has a name. It's called Simpson's paradox. And so what we'll see in the next slides is that it's actually not a contradiction. It's a misinterpretation of the data. So here I'm just bringing everything, all the information together. Here's the total population, this minus 14 from before. And here I'm displaying the males and females. And depending on which column you read, if you read this column, you get to conclusion 1. If you read these two columns, you get to conclusion 2. So that's the contradiction. Sorry, the word escaped me. So that's the contradiction. So how do we approach this? How do we resolve it? And this is how we could put in a graph, for example, do the treatment minus control of the population here, and then here you have per gender. So one way to look at this, and I love this visual, it was created by a data scientist friend of mine, Mark Platz. And what he did, he said, okay, let's split the control and treatment, their recovery rates by number of participants. So how do you read this? For example, focus just on the control. Here you have the two genders. Here's one gender, here's the other. But what's important here is the mean, okay, is this red bar over here for the control. So the recovery rate is that 70%, and here's the 58% from the treatment. And the reason these bars are different is because 80% of the control are one gender and 20% the other, and vice versa here. Okay, so this is this minus 14%, this minus this, that's minus 14. But the cool thing about this visual is once you color code it for the genders, here you have female and here you have males, now you see that it's going the opposite direction. It's going 10%. It's the same bars, right? But it's a different way of looking at it. So which is the correct way of looking at it? Well, what we have to do is we have to understand that the gender is an independent variable. It doesn't depend on the outcome or the group, drug or placebo. And so it's a confound that we have to control for. So the correct way of looking at this is these columns. Okay, so what that means is that this column here is actually nonsensical. It doesn't mean anything. It's meaningless, and it's just confusing, and it causes us misinterpretation. So we want to understand the story behind the data, in which the gender is a confounder that we want to control for. And the reason for that is because we can see that what we saw in the plot before is that the control, for example, was not this is not a randomized controlled trial for gender. They didn't take that into account, because here you can see it's 20% males and 80% females. And so what do we have to do? And here I'm introducing my first equation, just formalizing a bit. Instead of saying treatment minus control, we call that the risk difference. And so here's the risk difference per whatever group of interest. So this is a conditional probability. So that means, so here's the treatment condition on treatment, and here's condition on the control. And if you plug in these numbers over here, then you get this minus 14, 10, and 10. And here I'm just changing the label to risk difference. And so why is that useful? Well, how do we correct for this with the confounding factor? You've probably done this on your own. You probably solved for Simpson's paradox in your own data analysis, and now you're hearing it a bit more formally. But basically what you did is you did something called an average causal effect, or ACE for short. And what you did is you took the risk difference of each strata. So you took those are the females and of the males, and then you multiplied some weighting factor of that same stratum. Okay, so here I'm doing the risk difference of males and females, and that's how I get to, excuse me, an ACE of 10%. Okay, and so the visual is, this is a nonsensical result, the population. We want to focus our attention to the males, the females, and how do we aggregate them? Well, we aggregate them using the ACE and getting, as we could expect, a 10% as the average. So I had a disclaimer that I said I'm going to confuse just about all of you. I think I'm probably have been successful. I admit I'm the first to admit that I was very confused when I started out, and it took me about 3 weekends to truly understand this. And in the process, preparing for the study groups within my work, I actually created an app, and I'll just run you by this app, which is because the way I learn, I like to play around with numbers and shift them around just to see how a system reacts to them. And so what I set up here in this app, which I'll soon show you how you can access yourself. Here, I'm portraying all the information that you saw before in the slide. So here, the group, you have treatment control. Here you have the genders, male or female, and if they recovered or not. And here you have this visual from before, and you have also the mark plots visual as well. Okay, and so here we have also all the parameters required, so you can change these numbers at will just to see how the system reacts. Okay, so so here I'll show you one interesting case. So here I'm just going to expand so I can have more parameters. And so what I'm going to do over here is I'm going to say that there's no effect for the males. So let's say this is males over here. And so what I'm going to do here, going down from 80 to 70. So what we're going to see is this. 80 and 70. So these are now aligned. Okay, so what you can see here, interestingly, is the males, there's no effect. The females are 10%. So here, this is a nonsensical result from the population. My question to you is, what do you think the ACE should be? Right, the ACE should actually factor in both of these, and it should give some meaningful aggregate. So just if you have an idea, just feel free to put it in the chat. I'm just watching the chat to see if anybody has an idea how much the ACE should be. Thank you for sharing the app, by the way. Feel free to go in there. I don't see anybody answering, so I'm just going to give the answer. Very good, 5%. Yeah, so we expect it to be the average of just 0% and 10%, assuming a population of 50-50 of males and females. So we get the 5%. Okay, so yeah, so that's what first question that I had. I have another question for the audience. So why don't you try it on your own? I'll give you like 30 seconds to do that. How can we get the risk difference population to be equal to the ACE? So how can we get the risk distance population to be equal to the ACE? So meaning, how do we get this nonsensical one to be equal to that of the ACE? ACE is the average causal effect that we defined over here. Okay, so any answers? Okay, so I admit that it takes a long time to understand these things, but so one way to go about it is to there's a few ways. One way is to put the male treatment fraction to be 50%. Okay, because yeah, so I'm just going to refresh this. So if I put the male treatment fraction to be 50%, then they're actually even. Why is that? Because this is a true random control trial in which 50% male, 50% in females, and then we have all of them equal to 10%. Okay, there's another example I have in mind, but I'll trust that you go over it on your own time. I'm just limited at the moment. Okay, so I talked about Simpson's paradox. If you look at the literature, there's actually something else called Lord's paradox. It's actually the same exact thing as Simpson's paradox, just with different types of variables. With Simpson's paradox, we deal with Booleans. So remember that I had, for example, my treatment effect with either placebo or the drug. So in the case of Lord's paradox, we have something continuous, and so that's like continuous value of treatment. The outcome in Simpson's paradox was either recovered or sick, but here we're using something continuous. And so here, this is a nice visualization of Lord's paradox, because here you can see an apparent correlation between the two. The higher the treatment, the better the outcome. But if you aggregate by the age and gender, you can see that actually there's a deleterious effects for all of the cohorts. So I very much like this visual. So when I get confused with Simpson's paradox, I like to go back to this visual of the Lord's paradox so I can remember. So just in summary, take it from Bart Simpson. Simpson's paradox is a situation where you have a stark difference between your population outcome to that of the cohorts. And so you can, playing around with like the calculator that I created, you can get to very interesting and weird situations with the data. And so it's important to understand Simpson's paradox in order not to misinterpret your data. When you're designing an experiment, you should take Simpson's paradox into account. Otherwise, you might read your results wrong. And also, this is your first, if you're interested in causal inference, this is truly your first step. How to resolve this paradox? Well, we identified and we controlled for confounding factors. And most of causal inference is actually identifying and controlling for confounding factors. And that will be the main theme of the rest of the talk. So I mentioned randomized control trial. That's truly considered the golden standard for causality. The main limit, though, is that it can be expensive. It might not be ethical to do, and it might be also an artificial experiment that doesn't reflect reality. And so what we do have in most of our companies is observational data. That's much more accessible, and that's why causality, actually, the beauty of it is that you can save costs on randomized control trials, and you can address your observable data by understanding the story behind the data, how it's collected, in order to infer causality. Okay, so in order to do that, we said that we have to control for parameters. And one mistake is that sometimes scientists just control for anything they can think of, and they don't truly justify that. And one of the learnings from Judah Perls is that you do want to justify that. In order to do so, a very powerful tool is graph models. And that's our next topic, is visualizing the story behind the data with graph models. So you actually know what a graph model is, because when I did the ice cream and I did the smoke alarm and I did the lungs, I actually used graph models, and it was so intuitive that even if you haven't seen it before, you understood immediately what you were looking at. And here I'll just formalize what you actually already know. And so a graph model is each node is a parameter, and if two parameters have some sort of association between them, then you draw a line. If one is causing the other, you actually add an arrow. So in this example, for example, D is actually is caused by all of them, where actually you see a cycle between C and D. There's something called a direct acyclic graph, or called a DAG. It's a situation in which no parameter can go full cycle. And so this is a very useful tool that's used at least when you begin learning this field. And the reason this is useful is because you understand two main things. It helps you understand how the data was collected, and by doing so, you can infer the causal relationships between the parameters. And as a result, you'll be better in designing your experiments and getting causal conclusions from your data. And so here, when I introduced Simpson's paradox before, it was very confusing. I was using only words, but if you look at it with a visual, actually becomes much more intuitive. So let's look at the same pharma example I said before, but now with the graph. So here you can see that gender is independent from anything else, okay? It's not affected by anything. And the group is affected by the gender, right? We didn't have an even split between them. So which group you were in, if you were in a control or treatment, depended on the gender. And the outcome was a function of both. Okay, and so how do we resolve for Simpson's paradox? Well, we controlled for this confounder, right? This is the confounder, similar to the, when we had the ice cream sales in the drowning, we had the weather over here. Well, we controlled for it. So how do we control for it? Well, we can do it by two ways. We can either in advance, when collecting the data, doing a randomized control trial where we make sure that there's no correlation between gender and group. But if we have observational data, then we can use a trick like that ACE when we did the weighting of the parameters, that we can do what's called graph surgery and eliminate this using mathematical tools. So that's the beauty of it. Of course, one can raise the question, wait, this is very subjective. And my answer to that is, my experience in data analysis is that as objective as we want to be, at the end of the day, we're going to make a subjective decision. For example, if you have a distribution that's skewed, right, you have to decide mean or median, but maybe it's double mode, has two modes, and then you don't want mean or median, but you want to understand the story behind the modes themselves. So at some stage, the buck stops at the analyst, who has to make a reasonable decision that they can convince first themselves and then their stakeholders. And so that applies in anything, in statistics as well as causality. And yes, the graph model consists a lot of subjective decisions, but there are tools and ways in order to verify that your subjective decisions are correct according to the data. It's not 100% foolproof, but there are tricks that one can do to get some sort of sense that they're going in the right direction. Causality, it requires a whole lot of assumptions. It's beyond the scope of this talk to go through all of them, but I do want to emphasize that ignorability perhaps is the most important. And what that means is that you've identified all the confounders, that there's no other unmeasured confounders that you haven't thought of before. That's a massive assumption, but that's what's commonly used. So now I'll talk about justifying for controlling. Because before I said that some researchers control for all the parameters and they don't justify that. Let's see why that's important. Well, in this example over here, you remember it was a good thing to control for it because when controlling for Z, for example, here, we resolve for spurious correlations between X and Y. That's what we said before. But when do we not want to control? If we have something called a collider, like this parameter C over here, if we control for C, we actually cause a spurious correlation between X and Y. And that's something that you definitely do not want to do. And so what that means is you want to draw the graph and you want to see when you have forks and when you have inverted forks. So that's why it's important to draw the graphs in order to get these things. I don't have enough time today, but if you go into the slide deck and you go to Appendix 2, I show a nice example of a light bulb and two switches that control for the light bulb if it's on or off, and how if you control for the situation of the light bulb, you actually cause a spurious correlation between the two light switches. So it's well worth going over the slide if you're interested. So just to summarize justification of controlling of variables, we had common causes, like in the ice cream example, and so we wanted to control for it. We had also the smoke, in which we wanted to control for it in order to eliminate spurious correlation between X and Y. We also had that in the lung cancer example. And in the light bulb example, we actually do not want to control for these colliders. All right, so we're nearly there, nearly at the end. So we started off with seeing, we got up to, we started climbing our way towards doing. And later on, there's imagining. I'll spend the rest of the time just introducing these two topics, and then we'll talk about applicability, and I'll provide resources. And so when we start off our career in analytics, all we do correlations and associations, and basically that's the equivalent of a sentient that's only seeing the world. And seeing may be deceiving. And then we talked about sports correlations. We talked about Simpson's paradox. As sentients, we actually learned by doing, right? We put stones together and we saw that causes fire. And so by doing, we can actually, in terms of causality, what we can learn by doing, we can learn about causality for populations. And so by doing, I mean, we resolve for Simpson's paradox, right? We control for confounding factor. And so there's this whole field called do algebra, which enables you to do causality for on the group level, meaning for, let's say, for all males within an age bracket, you can learn about how effective a drug is. The next step in the ladder is imagining. So that's creating what-if scenarios in which you can answer for an individual. And for example, so instead of for an age bracket between 30 to 40 of males, how well a drug will work, you could do it for your own cousin, okay, who's age 34. You can apply it to them. And so that's a topic called counterfactual, how your cousin would react if taking the drug or the placebo. That's a very high level idea of these topics. So now I'll talk about them a bit more in detail. And so in doing, what does doing mean? By doing, we're actually intervening. We're actually doing a change in the system. So I like this graph by Neil Brady, in which he shows if you have a population and you split them into two populations, you have the treatment, for example, drug, and you have the placebo with 0. So what we do in seeing is most of our analysis is on conditioning, right? This is what we observe. Intervening means actually, no, you want to apply on the whole population. You want to give everybody once, you want to give them the treatment, and everybody once you want to give them the placebo. This is a theoretical notion. You can see where I'm going with this, right? Because you can't do this in reality. But that's what causality requires us to do it for everybody. So obviously, we can't do that in the real world. And so when I talked about the whole do algebra, it's a whole beautiful mechanism of tricks and using intuition and the story behind the data for going between this intervening to what we want to have ideally to what we actually have access to in the real world, this conditioning. And so this process is called causality identifiability. How do I identify between the theory to what you have actual observable? Okay, so what we did before is, well, this is what we want. This I'm introducing this do algebra. Okay, this is an operator that you're probably not familiar with, but it's an operator that you apply, and that's you apply in a system like this. Okay, and we talked about graphic surgery in which we eliminated this arrow here. So that's going from this sort of graph G to a modified graph GM. And so what you're doing is you're converting between the probabilities in this graph to probabilities in a modified graph. I admit that's a bit abstract. I think I'll skip this part due to lack of time. Yeah, but it is a fascinating topic. And again, that's in order to get causality for a group. But what if you want for a specific individual? And so what you want is something called a counterfactual. You want to test something with the drug and with the placebo. So of course, so that leads us to what's called the fundamental problem of causality. We don't actually have access to counterfactuals in most settings, right? You cannot give everybody both the drug and the placebo. And so how do we resolve for this? Well, actually preparing for these slides, I actually took a critical look into this comic strip, as ridiculous as that might sound, and actually realized that this is a counterfactual. And so I'll run this logic by you, where this is a case actually where you do have a counterfactual. So you remember at the beginning of the talk, I said, this is in this conversation, she asked, was the intervention successful? And he was inconclusive. But actually, he should have been more conclusive. The reason for that is the outcome is that he thinks the correlation causes causation. So that's either a binary, true or false. So the factual is he started out thinking that I should have mentioned the treatment is doing a statistic course or not doing a statistic course. So in actual fact, he did do the statistic course, so that's a true, and the outcome was false. He did not think anymore that correlation caused causation. But we do know the counterfactual. He admitted himself, if he wouldn't have taken the course, if he would have taken the course, treatment is false, the outcome would have been true, okay? So that means the fact that he took this treatment for him specifically, that actually change the outcome. And so here we actually, in XKCD, we have a case of counterfactual. So I was quite happy when I noticed that. So the main question you probably have in your mind is, well, can I apply it or not? We talked about all these assumptions. We mentioned the fundamental problem of causality. And yeah, it's not always applicable. When is it applicable? Well, if you have simulated data or highly controlled for example, in random control trial, where you control for gender and everything else that you believe should be controlled for, then causality is likely to be applicable. In a lot of real world data, where we can't adhere to all of these assumptions, then you might not be able to. And so my approach is kind of like, know what your limits are. Like, address any question in mind in evaluating how applicable causality is. Because yes, of course, it might not be, but you should be educated enough for your stakeholders to suggest, like, maybe something's missing and you can design for a better experiment in the future so you get a causality at the end. And of course, you want to avoid misinterpreting your data when analyzing the results. Further inspiration, the last Nobel Prize for economics went to researchers that applied causal inference to natural experiments in the field of education. So just to bring everything together, here I'm just updating William Deming's quote. It's not enough to bring the data, you also have to bring him the story behind the data. And the reason for that is that the story behind the data is as important as the data itself. You want to understand how the data was collected, and you want to understand the relations, and you want to understand the true relationships between the parameters. How do we learn that? Well, we talked about the fact that by understanding the story behind the data, it will enable us to avoid misinterpretation of the data. The classic examples are Simpson's paradox and spurious correlations. We learned the fact that graph models are powerful tools to visualize the story behind the data. And it's a way for us to justify which parameters we can control for. So what's next in your journey? Well, I suggest feel free to use my calculator. You do want to master Simpson's paradox, and it might take a while. Again, for me, it took 3 weekends to fully appreciate, understand it, and I needed 2 study groups in order to convince myself that I truly understood it. And then once you're ready with that, go on, do algebra and counterfactuals in order to do causality on cohorts and individual levels. I'll soon share my resources, but first I do want to thank the doodle master, James Barker, who created these beautiful visuals that kind of really make this interesting topic more accessible. I will shamelessly also promote 2 other talks that I have, in which you have the links to. The first is Improved Decisions Using Pareto Fronts. And where that's useful is if you're interested in optimizing for 2 or more parameters, and they might be in contradiction, or they might be uncorrelated, like this, for example. How do you define, how do you optimize for that? Well, that's what I get into in this tutorial over here. And for those who are interested in hypothesis testing, I have this talk, Don't Stop Till You Get Enough. It's to understand how much data is required to collect in order to significantly statistically interpret your results. So in other words, demystifying the dark art of hypothesis testing. So you have the links over here. As per resources, I went through both of these books. So this is a great layman book. This is what I actually used for the study groups. And these were also recommended by colleagues of mine, which I went through, and they look quite good. So I recommend these. I also highly recommend Neil Brady's course. So first of all, it's free. He's actually trained on the topic. He clearly explains many aspects, and he interviews lecturers, experts in the field, and he has like reading papers to go through. So that it's probably the most valuable resource online for this topic. So I highly recommend it. In terms of playing around with causal models, I recommend Daggety. So within it, you can sketch your own, and you can learn about the relationships between the parameters, what you can and cannot do given your system. So it's a highly valuable tool, also free online. A few tools that I created. Sorry, so for those who use Python, I created a notebook just to run through the same example, in which you'll use a module called pgimply. So if you're interested, you can either download it on Git or use Google Colabs. And I also have a few blog posts on the topic if you're interested as well. And so with that, I will take questions. Thank you.
Fantastic. Thanks very much, Eyal. Really interesting stuff there covered. I think there are loads of topics I'm sure grabbed everyone's attentions. I think, as mentioned in the chat, if anyone's got any questions, I'm sure a lot of you have, so feel free to put them in the Q&A now, and we can work through them over the next 15 minutes before we close. But maybe I'll start, kick things off then. You mentioned when causal inference might not be applicable. I was curious to know what could be considered the converse of that, or when it's been absolutely necessary, and particularly if you've got any stories to tell on any examples where you felt that there's no other option but to use causal inference from your experience then.
So the first thing that comes to mind is you have a fully deterministic system in which you have full control over the levers. So for example, I can't go into details, but in my work, like on the Simpson checker, there is a component where I am working with something very deterministic. It's basically rules that go in. The Simpson checker is probabilistic in nature, but we have overriding rules, and those are nearly fully deterministic, and I have a switch. I can change the rules however I want just to see how it changes. And so that I consider a counterfactual, because a systematic counterfactual, I can change a whole bunch of rules to check the implication of changes of the rules. So I found that very useful in my line of work. So to answer your question, one aspect is if you have a fully deterministic like set that you have full control over.
Great, thanks, Eyal. We've got a question coming in on the Q&A from Pastor Lee. The question is, are there any automated discovery tools to generate the graphs that you showed from data itself?
So that's an excellent question and quite valid. It is, so automation has, I have to remember that anything that's automated has assumptions made by engineers. If those engineers did not know the story behind the data, that automation is not useful. So you always want somebody, some domain expert who can correct for any assumption that's made incorrectly. And yeah, that's the way I think about it. Again, the emphasis is the story behind the data is as important as information. And you saw how easily, like, just with the light bulbs, with the light bulb example, you had a collider that if you control for the collider, you automate that by accident. You're going to get wrong results. And so, yes, I agree that automation is a great thing, but the story behind the data has to be implemented by domain experts. So I'm a fan of, automation along with human intuition.
Great, thanks, Eyal. Perfect. I think there's another question coming in from Tariq, who said, great talk. The first time I understood the Simpson's paradox. However, I don't understand counterfactuals. Could you have one more go at explaining in plain English? Sorry for being thick. I'm sure it's not a thick question. I'm sure there are many people out there who are thinking the same. So yeah, counterfactuals, Eyal, how might you go explaining about that?
Okay, what's his name?
Tariq.
Tariq, okay, so I'll use a counterfactual on your situation today. So you just said, if I heard correctly, that this is the first time that you understood Simpson's paradox, right? So your counterfactual would be the outcome is you understand Simpson's paradox, true or false. Before this talk, you did not know Simpson's paradox, right? The intervention is you actually went online and you listened to this talk. That's your treatment, right? And so the question is the intervention, right, this treatment of attending this talk, did that change anything? Did that change the outcome? As the answer is yes. For you as an individual, Tariq, attending this talk is caused you to understand Simpson's paradox. So that's the counterfactual for Tariq, right? If you wouldn't have attended, you would have continued not to understand Simpson's paradox. At least until the next time you heard a talk on the topic. That works for you, Tariq. But if somebody else, let's call her Mona, for example, let's say she still doesn't understand Simpson's paradox, then the same exact intervention did not work for her. Okay, so she had a counterfactual world in which she didn't attend it, and she still wouldn't have understood it. Okay, so the counterfactual is not attending this talk. That's the counterfactual. And then I just gave an example, like in the XKCD, in which, just pull it up here. It's the same example that I gave here, is that by attending the class, that's his counterfactual. Sorry, the factual is attending the class. The counterfactual is if he wouldn't attend the class. So that's a hypothetical what if case. That's what a counterfactual, it's something that deviates from what actually happened. I hope that helps. I do admit that can be confusing, but. Yeah.
Cool. Any call for any final questions? Feel free to post them now. Just one more from me, Eyal, as well. And the average causal effect that you mentioned as well, really interesting. I was curious to know, will that still hold for more than one confounder? So is that still applicable in the case of multiple confounders? Or is there an equivalent that can be used in that case?
Yeah, most definitely. I refer you to this book over here, in which he gets into all the equations and everything you need to know to address ACE in other metrics of causality. And I talked about identifiability, and that's our linking between what we want in the ideal to our actual observables. Our observables not only are conditioned probabilities, and if we can, through our graph models, which visualize the story behind the data, we can link between what we want ideally to our actual observables. And so yes, we can do that for more than one confounder.
Fantastic. Thanks very much.
So chapter 3 in this book, you learn all about that.
I will take a look. Thank you. Great. We've got one more question coming in, so maybe if we make this the last question. Jack, thanks very much for the question. So Jack's question is, for cohorts with many different methods of segmentation, how would you have confidence that you have managed to identify and control for all the confounders? Are there any methods to do this?
Yeah, so that's kind of like a reiteration of Nicholas' question. There is a whole list of mechanisms. I don't have them on the top of my head. I do have a colleague that he had a whole list of mechanisms for, I'm forgetting the term. Sorry, let me just look it up offline here. Sorry, propensity scores. Yeah, sorry, it escaped me. So yeah, so propensity scores is one way to have full confidence. You know, the more the finer the segmentation, the more data you need, so the less statistically significant it is. And so I always worry about those things. And so at the end of the day, you know, keeping things real, you want to keep it as simple as possible. But just the brief answer to the question is you want to look into propensity scores. Yeah, to get a general feel for how to address these.
Fantastic. Hopefully that answered your question, Jack. And I didn't see any more questions in the Q&A. So thank you very much, Eyal, first of all, for the great talk. Really fascinating stuff. I really appreciate it. And thank you, everyone, for joining.
Thanks, Nicholas.
Thank you all.